Noise is incredibly useful when it comes to writing shaders. Whether you are generating a terrain, drawing abstract contour lines, or simulating fire, you are likely to include noise in your work. In this video, I'll show you a simple image transition example that uses noise to spark creative ideas for other applications. This tutorial assumes a basic understanding of how to use Three.js with custom shaders. Check out my Three.js tutorial series in case you need a jump start. I'll be working in a Vite project. To create a Vite project, you use the command npm create Vite and npm install 3 to install Three.js. Here is the basic HTML I'm working with. The body has a black background and no margin. I also have two shader files, the fragment shader and the vertex shader. To use shaders in a Vite project, we need to create a vite.config.js file. This file is going to allow us to import shader files in our JavaScript. Add this code to the config file. In main.js, we import Three.js and our shader files before setting up a basic scene. Since we are only displaying images, we use an orthographic camera. This camera takes 6 arguments. The first 4 set the left, right, top, and bottom boundaries of our viewing frustum, and the last 2 are the near and far planes. An orthographic camera shows objects at their true size without perspective, which means you can move the camera along the z-axis without affecting the scene's appearance. We create a plane on which we will draw our images at the origin. Since the camera cannot also be at the origin, we move the camera along the z-axis. Next, we create an array of images and use the texture loader class to load these images for our shaders. The plane is sized with a width and height of 2, perfectly covering the camera's view. The material for the plane includes both the fragment and vertex shaders. Its uniforms contain 4 items: the current image, the next image, the texture uniform called uTexture, and a boolean flag called renderMask. In order to understand why we need these variables, let's talk about how the transition works. Consider what we call a mask. Think of a mask like a green screen. Specific colors, in our case black and white, determine which parts of one image are replaced with another. Here, white represents the current image and black represents the next image. The white area starts as a small shape at the center and spreads outward, gradually filling the screen with the next image. But how do we get these ink spread effects? This is where noise comes in. We use simplex noise, which smoothly varies between pixels without abrupt changes. We start with a small white rectangle at the center, then determine each pixel's color by checking the noise value at that coordinate. The noise value gives us the magnitude of a vector pointing towards the center, and the pixel where the vector lands determines the final color. If it lands on white, then the pixel is updated to the next image, and the current image if it lands on black. So you can see how the brighter regions in simplex noise are going to be updated earlier with the next image since the vector has a larger magnitude. We render the image twice, once to save a copy for the next render, and again to display it on the screen. The initial image is rendered in a separate scene with a centered rectangle. We use the WebGL render target class to hold the rendered mask, using 2 targets to prevent conflicts when modifying pixel values. Inside the animation loop, we first set the mask texture to the current render target. This flag tells the program to output this texture, which is the next render target. Then we set the render mask flag to false, so the fragment shader displays images on the screen using the current mask. Setting the render target to null directs the output to the screen. We also swap the render targets to reuse the current mask texture in the next render. Every 5 seconds, we perform an image transition by resetting the mask to the initial centered rectangle, updating the current and next images, and advancing the image indices. Let's also quickly handle window resizing before moving on to the shaders. The vertex shader is straightforward. Because we're using an orthographic camera without any extra transformations like scaling, rotation, or translation, we set the pixel position directly. We pass the UV coordinates, which represent the pixel positions, to the fragment shader using varying variables. In the fragment shader, we receive the current and next images via uniforms from JavaScript. We also import the mask texture and a flag indicating whether to render to the mask texture or the screen along with the UV coordinates. Now let's go ahead and add our functions for generating noise. And I'm using the noise code from this GitHub repo. In the main function of our shader, we obtain the noise value at each pixel using the FBM function, which stands for fractal Brownian motion. This function takes the UV coordinates and the number of noise layers or octaves as its arguments. The more octaves you add, the more detailed the noise becomes. I multiply the noise value by a small constant to keep the sampling near the current pixel. You can adjust this value for a faster animation. We calculate the vector based on the noise value to decide which pixel from the mask to sample, and then we extract the pixel's color with an offset determined by that vector. The uTexture variable holds the mask from the previous render. Keep in mind that in each update loop, there are two render passes. The first creates the mask for the next frame, and the second displays the final image on the screen. The images are blended based on the mask's color. White regions show image 1 and black regions show image 2. And that's it, a smooth image transition driven by noise. I hope you found this helpful. My name is Francis. Thanks for watching, and I'll see you in the next one.